Welcome. My name is Julie Gunkelman, and this is the 2016 AMATYC webinar series. We are so lucky today to have Herb Gross with us for a second time. And it is the webinar series, and groundbreaking as it is, If I Knew Then What I Know Now, a three-part webinar series. And today is the Game of Algebra. The Developmental Mathematics Committee is sponsoring this presentation. One of our core values at AMATYC for professional development is building expertise and exhibiting leadership in the enhancing and learning, teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. And that, of course, is why we are all here today. Please see amatyc.org for more information. Please note that the views expressed by the presenter are not necessarily the views of AMATYC. Commercial products mentioned by the presenters are not endorsed by AMATYC. And that's not going to happen today, but I have to read it. The webinar is sponsored by WebAssign. Thank you very much, WebAssign. Instead of reading a biography, if I did that, it probably would take the entire hour because Herb has done so much. I'm going to shoot you guys a link to look at the AMATYC President's page. Herb is our founding president of AMATYC, and there's a lot of information about things that he's done, and I can share that with you after the webinar today. I'm going to go ahead and switch this over to Herb. I'm going to go ahead and mute myself so you don't hear me moving around at all. Without further ado, Herb, take it away.
Hi, I'm just thrilled to be with you all. And I imagine I have a few back from last time and maybe a few new ones. I haven't heard from anybody, which I'm going to take as a sign that no news is good news and that nobody was too upset by the format or the content of what we talked about last time. Basically, what I talked about was how I might have viewed things differently if at the time I got the vision for forming NISMATIC and AMATYC, calculators and computers were already available and the internet. And I think last time I limited to the study of arithmetic, and this time I would like to extend it to perhaps how we should be teaching algebra and the like. Whenever I give a talk, or even in class, I always like to start with some sort of an anecdote that's funny enough to make the audience laugh, and at the same time pointed enough so that once they remember it, it leads into the talk. And I remember the story of the young man who had a very, very noticeable stutter. Somebody said to him one day, "Sam, how are you doing?" And he said, "Fine." They said, "Gee, you have a terrible speech impediment. You want to do something about it." He says, "I do." They said, "What do you do?" He said, "I go to a special speech school." I said, "They go to a special speech school." They said, "Did that school teach you anything? Because you still have a terrible stutter." He said, yeah. They taught me to say, "The rain in Spain falls softly on the plain," but it never comes up in conversation. And basically, I think this fits into the student who says, "Where am I ever going to use this?" The English lit major who says, "Where do I need the quadratic formula?" In fact, I remember a joking definition of algebra as an in-depth study of the last three letters of the English alphabet. Many of the students who are taking math are just, say, taking developmental algebra. They're just thrilled to pass the course. And they say to me things like, as I just said, "Where am I ever going to use this?" And I give them a sports analogy. I say, football players do maybe 100 push-ups a day practicing to play a game. But in the game, they don't do a single push-up. Yet no player has ever said to a coach, "Coach, how come we do 100 push-ups each day in practice, but we never use them during the game?" And it's because the players realize that the strength that they get from doing the push-ups is going to help them perform better in the game. Now, in that sense, I look at math, algebra, calculus, anything, as being the calisthenics of the game of life. That you don't use the algebra per se, it's the critical thinking that you learn from it. Okay? Now, here's what happens. When we say that calisthenics is very important for a football player, it doesn't mean that all calisthenics are equal. In other words, a calisthenics that's good for a football player might be bad for a gymnast and vice versa. You have to make sure that the calisthenics you're using actually follow your claim that this is the calisthenics in the game of life. Now, for example, if all we want to do is teach the kids how to solve algebraic equations, invest a few dollars and buy them an optical scanner. As I understand it, you put the scanner over the equation and it will print out the solution step by step. What the scanner won't do is to show you how the equation was derived and where and when it's applicable. So let me just give a few examples, and this will explain why I call this lecture the game of algebra. You see, the important thing in algebra is not that you get the answer to a John and Bill marble problem. Look, if you say John and Bill together have 100 marbles and John has 20 more than Bill, you don't even need algebra to solve that problem. You simply say something like, you know, if they each had the same amount, 50-50, and we took 10 away from one and gave them to the other, that would make up for the 20 difference. And so right away you see if the answer is 60 and 40. The beauty of algebra is to say, in real life, how often are those going to be the numbers that you're using? So all we do in algebra is instead of saying 100, we use a letter like T for total, and a letter like D, with my diction, I hope they don't sound too much alike. Tom, the T, and Dave, the D. And instead of using 120, we use those letters and using just a few rules of the game. And by the way, that's the other thing I do, is instead of calling them axioms, I say we're going to play the game of algebra and I'm going to give you the rules. And all the rules are the field axioms. Okay? Using there's 3 steps in that algebraic procedure. You know, if J is the number of marbles John has, and B is the number Bill has, and T is the total amount, from J plus B equals T to J minus B equals D, one discovers that all you have to do is take half the sum of those 2 numbers, and that will be what John has, and half the difference will be what Bill has. In other words, as soon as you look at that problem and you understand this, you can now solve this problem no matter what numbers they give you. In other words, with algebra, let me see if I can word this in a way that doesn't even involve math. Let's suppose I'm teaching geography, and I want to see, using a fill-in-the-blank question, whether the students know that Sacramento is the capital of California. One way I can word it is to say, Sacramento is the capital of blank. I can also say blank is the capital of California. Depending on which one of these 2 I use will affect how the students perform. For example, if I say Sacramento is the capital of blank, the kid might say, gee, I didn't know Sacramento was the capital of anything, but I know it's in California. So I'll take a shot and say it's California. On the other hand, when you say blank is the capital of California, the only proper noun they see is California, and I don't think Sacramento is the first name that pops into their mind. And you say, okay, I understand that. What's that got to do with algebra? Well, today, kids have calculators at home, in their car. I mean, they're clearly a household item. Okay? When we want them to compute something, we sometimes say to them, you can't use the calculator. But of course they have the calculator, they can use it. Especially in an algebra course, because they've already passed arithmetic, and that should make them eligible to use a calculator for algebra. And what algebra is, the game of algebra, is how you arrive at certain conclusions that follow inescapably from the rules of the game. If you look at the field axioms, the only 2 numbers that are mentioned by name are 0 and 1. Where did the rest of the numbers come from? Well, they have a rule that says the property of closure. The sum of any 2 numbers is a number. Great. If 1 is a number, so is 1 plus 1. We'll call that 2. If 2 is a number, so is 2 plus 1. We'll call that 3. If 3 is a number, 3 plus 1 is a number. We'll call that 4. If 4 is a number, 4 plus 1 is a number. We'll call that 5. And we go on that way. All of a sudden, somebody says, how much is 3 plus 2? Well, we know, hopefully, that that's 5. But the way the game is played is you have to be able to show that just from the rules of the game. And that's where the commutative and the associative properties come in. You rewrite 2 as 1 plus 1. So 3 plus 2 is 3 plus 1 plus 1. Now by the associative property, you can group 3 plus 1 together. And by definition, that's 4. So now that's 4 plus 1. And by definition, that's 5. Now, that sounds like an awful long way to prove it. But what we're doing when we're trying to teach people algebra is logic. You can only assume, you can only use what everybody in the room has accepted as the rules of the game. Okay? For example, in what are these problems? Share the work problems. John can paint the fence in 6 hours. Bill can paint the same fence in 3 hours. How long does it take if they paint the fence together? You have some students who say 9 because they just add the 3 and the 6. You have others who average the 3 and the 6 and they say 4.5. And obviously the answer has to be less than 3 hours because working alone he can do it in 3 hours. Bill would have to be a very destructive force if it took longer when John was painting with them. Now, I'll exaggerate slightly here, but it's amazing. I'll exaggerate a lot, all right? You say to a kid, you give the kid this problem, and he says, it'll take him 4.5 hours. I say, look, if the faster guy can do it in 3 hours by himself, how can it take him longer if he has help? He says, well, they talk to each other, maybe they take a coffee break, and all of those things are possible, but they're not included in the problem. And by the way, if you think it's a student who makes these mistakes all the time, the textbook author does the same thing. He says things like, and I'm generalizing again because I haven't looked at all textbooks, if John can paint the fence in 6 hours, in 1 hour he paints 1/6 of it. Well, who paints linearly? Is it possible that he painted very fast the first hour and started to get a little bit tired? Mention that you're assuming that he works at a constant speed. In fact, instead of having John and Bill painting fences, have 2 water pipes where the water flows through the pipes at a constant speed. Because at least that way you can say, if the pipes fill it in 6 hours, in 1 hour they do 1/6. I used to love to give the kids the problems like John can eat his breakfast in 12 minutes, Mary can eat her breakfast in 18 minutes. How long does it take them to eat their breakfast if they eat it together? See, there are all kinds of assumptions that are going on. What if the 2 painters have only 1 paintbrush? In other words, there's a lot of places that we could be showing people what algebra does and what logic does by basically making sure that we let people know what assumptions are being made. And another thing that algebra does, that trial and error doesn't do, and I usually pick the numbers here pretty carefully. Let's look at the equation x squared minus 3x plus 2 equals 0. And I say to the kids, let's solve this equation by trial and error. Well, we plug in 1. I said, we'll just use whole numbers. We plug in 1, and we get x squared minus 3x plus 2. Turns out to be 1 minus 3 plus 2, which is 0. That checks out. Okay, good. Now I'll try 2. Well, x squared becomes 4. 3x becomes 6. So it becomes 4 minus 6 plus 2. That's also equal to 0. Now I say to the kids, look at that. We only tried 1 and 2, and we already got answers. Let's look for some more. This is a lead into factoring. In other words, I want them to see that you can keep looking and you're not going to find any more. Here's the problem. When you can't find any more, does that mean there weren't any? Or does it mean that there were, but you just weren't clever enough to find them? The same thing with an incurable disease. is it really incurable, or is it curable, but we haven't found the cure yet? And until you find the cure, you can't answer that question. Okay? You follow the line of thought here? See, when you rewrite x squared minus 3x plus 2 equals 0 as x minus 2 times x minus 1 equals 0, you know that the only two solutions, it says that either x is 2 or x has to be 1, otherwise there's no solution. So now this is the stuff that we should be emphasizing. In fact, when we say, let's check our answer, the check is part of the problem. All you've done in an if-then statement is if you've shown the only survivors of what the then can be once you're given the assumptions, you've eliminated all the possible wrong answers, but you still have to check whether the two survivors fulfill the conditions that were asked in the problem. So we have, excuse me, this happens every so often. This even applies to calculus. You know, I was talking with Julie before we went on the air. One of the things that bothered me, and maybe it's changed since then, that most pre-calculus courses that I've seen don't stress the most difficult concept that the kids find when they come to calculus, and that's the limit concept. They get to calculus and they get overwhelmed by epsilons and deltas, and if little n is greater than capital N, etc. Well, the calculator also helps make it easy to grasp what instantaneous means. For example, again, working in terms of the game idea, we make up some rules of the game for instantaneous speed. See, this is an interesting paradox. We all sense that at any given instant that the object is moving, but if the time duration is 0, no motion takes place. If no time expires, no distance is covered. So the ironic thing is, and this is why you get these paradoxes, is that we know the object is moving, but that at any instant it's standing still. So we make up some axioms. We say, for example, the axiom for average speed, the total distance divided by the total time. We make up the axiom that says there is an instantaneous speed. And then we make up the rule that if an object is accelerating, its greatest speed is at the end of the interval, and its least speed is at the beginning of the interval. And just based on that alone, you can answer, even in the 5th grade, give a 5th grader a hand calculator, and here's the problem you should be able to solve. An object is moving along the x-axis according to the equation x equals t cubed, where x is in feet and t is in seconds. How fast is the object moving at the instant the time is 2 seconds? You say, okay, I don't know if it's moving at all at the end of 2 seconds. My axiom tells me that it does, but what I can do is I know that at the instant it's 2 seconds, that's the fastest speed that the object had on the interval from 1 second to 2 seconds, but the slowest speed it's going to have on the interval from 2 seconds to 3 seconds. Well, it's easy to compute the average speed between 1 second and 2 seconds. Okay, you just plug those numbers into x equals t cubed, and you wind up with it was moving at 7 feet per second. And since that's the fastest, since the object is moving the fastest at the end of the interval from 1 to 2, we know that the speed is more than 7 feet per second. On the other hand, at the instant t equals 2, that's the slowest speed it's going to have on the interval between 2 and 3. And the average speed there, using again x equals t cubed, is 27 minus 8, it's 19 feet per second. So right away, here's what we can say. The instant speed is exactly some number that's between 7 feet per second and 19 feet per second. Well, there's a lot of numbers there, okay? But at least now we have a range. Chris says, yeah, but that's a pretty big range. Fine. The interval didn't have to be between 1 and 2. It could have been between 1.99999 and 2. Remember, before the calculator came into existence, it's not easy to raise 1.9999 to the 3rd power or the 4th power or the 5th power. Now it's very easy with the x to the y key. So you can compute the average speed between 1.9999 seconds and 2 seconds. It'll come out to be something like the 3 decimal place accuracy. Well, I won't even say 3 decimals. It'll come out to be something like 26.9999 something. Then you can do the average speed between 2 seconds and 2.0001 second. That turns out to be something like 27.00001. Well, now you can actually see this gap really getting small. And if a person didn't like that gap, they could pick even a smaller distance. If you know that the speed has to be more than 26.9999 and 27.0001, you can say measured accurately to the nearest thousandth of a foot per second, it's exactly 27 feet per second. You see, and we can go on and on that particular way. And what I'm saying is, when the kids see these actual numbers, that has a lot more meaning to them than epsilons and deltas, but the transition from there to the epsilon deltas is much easier. For example, even when you talk about the point 2, 3 on a graph, notice that the point that you made has thickness. It's not a point. Remember, Euclid calls a point that which has no parts. And if you can see it, it means you could have seen half of it. Okay? Actually, it's a disk. And in that disk are a whole bunch of numbers that are very close to true. And that's where that epsilon comes in, and stuff like that. What I'm saying is it stops being that abstract because they've built up an intuition because they've seen these things with numbers. Okay? Well, in the interest of time, let me drop that part of the subject for now. Hopefully, you may be getting some ideas now on how we should be teaching algebra or any math course, taking full advantage of the technology that exists. The problem I've found is that most of the technology is still geared to, this is how you do this problem, this is how you do that problem. I think Khan Academy, I may have mentioned this in the last webinar, does an excellent job on that. But he, nor any of the others that I've looked at on the internet, talk about the why. They talk about the how. And my contention is that when the kids can internalize the why, the how becomes much easier to use. But now we come to that student who isn't interested in a math science career. And we have a lot of them. Maybe at your own community college. I used to do little surveys on this when I was actively teaching, and I was in the community college classroom for 40 years, even though my big reputation seems to be based on the 5 at MIT when I made the Calculus Revisited series. I would estimate that upwards of 70% of the students are not interested in the math science career. And if you force them to take algebra in the usual traditional way, and that English lit major says, where am I ever going to use the quadratic formula? In the old days, at least, you could say, well, you're young, maybe you think you're going to be an English lit major, but you might not be. Just learn this because you might need it someday. I can't say that to the student today. All that student has to say to me, look, I have great faith in my major. I'm sure I'm going to be okay. But if God forbid I'm not okay, I'll Google the quadratic equation if I need it. See, these are the things that are available. So somehow or other, at least in my mind, we have to teach mathematics. We have to invent, or not maybe invent, but improve on what we call math appreciation courses. In particular, for the type of student who is weak in algebra, doesn't have the prerequisites to go into what is currently called a math appreciation course. I think a lot of places are using statistics as a substitute for math appreciation. What we have to do is to show them a course that will relate to what they're studying. For example, let's look at mathematics through the eyes of the humanities and social science. In fact, the title of my first textbook. I call it Publish and Perish. What's called Mathematics, a Chronicle of Human Endeavor. By the way, I believe that either has been or soon will be available on my website. But it's a course that I believe any humanities and social science student can benefit from. Because what it does is it traces the growth of a civilization viewed through the eyes of the development of place value. Most books, most courses, even in elementary school, they start off teaching the kids the numbers. They don't talk about the great achievement that took place between the time cavemen were first drawing pictures on walls till the time we actually developed place value. It's a great saga, and we don't teach it. And when you do teach it, people suddenly understand why place value works. They understand different number bases, etc. You see, what are the criteria for society development? I have like 3 axioms. One is that people look for the simplest solution to any problem that plagues them. And they look for a more complicated one only when the simpler one either becomes too cumbersome or is proven to be incorrect. Okay? And even then, they look for a correction that's as simple as they can find. Sort of imagine people going along on a flat plateau, everything is fine, and they come to an obstacle, a high mountain. To get to that next plateau, they have to climb that mountain. They have 2 choices. They can either elect to stay at the plateau that they're on, or they're going to have to find a way to scale that obstacle. When they decide to scale that obstacle, once they scale it, they have a good news, bad news story. From where they are, they can see better than the people who are stranded at the plateau below. That's the good news. The bad news is, from where they are, they look ahead and they can see the next obstacle, which isn't even visible to the people on the plateau below. And in fact, this is how society progresses. You go along smoothly, you hit an obstacle, you overcome that obstacle, you move on level plane again, come to another obstacle. And in fact, this is how I see the correlation between religion and science. The question comes up, do you eventually reach a plateau where there are no more obstacles? In many religions, we call that the coming of the Messiah. I'm not going to get into that at all. The point I'm going to bring out is that as a scientist, you say, how do we know this is the last plateau, or whether the next obstacle is so far away we haven't seen it yet? In other words, no matter what religion you have, in the real world, you live probabilistically. In other words, there may be a predestination thing, but we don't know what it is. But I won't dwell on that much. Let's put it this way, in terms of those plateaus. Each generation inherits a legacy from the past, and in turn, leaves a heritage for the future. I think it was Newton who epitomized that very nicely when he said, if I could indeed see further than all those around me, it was only because I had the good fortune of being able to stand on the shoulders of the giants who came before me. Okay? In other words, each of us inherits a whole bunch of things that we did not know otherwise. People have made sacrifices to get us to where we are today. I think anybody can appreciate that. So how do we do it in math? Well, one way is just to emphasize how place value came about. In other words, you start with these pictures on a cave wall, we call them hieroglyphics. After a while, people discovered that, hey, you don't have to draw the picture, just draw a tally mark. And it took many, I think, centuries between the time people were drawing pictures and realized they could represent the object by a tally mark. And you would have to guess what the tally mark represented by the context. Well, that was great. People could now do all kinds of things with tally marks. I think we talked about that a little bit last time. I'm not sure. I'm not even sure about what I talked about so far today. But basically, after a while, it became very difficult to tell the difference between a stack of even small numbers, 14 tally marks or 16 tally marks. That's where one-to-one correspondence came in. You can count without knowing how to count. If I've invited a certain number of people to come to my house, and I want to know if they've all arrived, to say it's a dinner party, I have one chair for each person. And if the chairs get filled and nobody is left standing, it means that everybody I invited showed up and nobody else did. If I have empty chairs, I know that some people haven't showed up yet. And if I have too many chairs, I know people showed up who either I forgot to invite or they decided to come anyway. And so that's where Roman numerals came from, etc. Well, why did we get rid of Roman numerals? Well, we replaced that by the abacus because you had too many denominations as science grew. Okay? And what happened? Even with the abacus, you could tell what a bead represented just by what wire it was on. Essentially, place value came in. What was place value? It was the first system that we had where you couldn't tell what the number modified just by looking at it. In other words, there were no visible nouns. Even the abacus had visible nouns. And what happened with place value? We were able to proceed so far with science that we eventually had to use scientific notation. For example, in Avogadro's number, it's what, 6 times 10 to the 23rd? That's a 6 followed by 23 zeros. The number of zeros became as cumbersome to count as the tally marks became cumbersome in primitive times. Will we eventually need something that goes beyond exponential notation? Time will tell. But these are the kind of things that we can be doing for the humanity and social science major who are weak in math, and it will even help the student who's good in math. In other words, you don't have to know much math if the whole course is going to be developing place value. Okay, so that was the first assumption. The second assumption is that man alone, I guess I shouldn't say man, because man in those days was meant men and women. Humankind alone, at least to our knowledge, is the only animal that can plan and predict the future solely on their knowledge of the past. In other words, that we alone are able to use logic to make certain deductions. And that again comes back to the game of algebra. If you're going to do algebra, don't worry so much about the student becoming good at math. Worry more about them learning to appreciate it and not being afraid of it. That's the really important thing for kids who are not going into a math science field. Now, you can make up a logic course in other ways too. It doesn't have to be just algebra. Or if it was algebra, why not Boolean algebra and restrict it to the and/or, in other words, grammatical structure, implication, conjunction, disjunction, whatever. Because how then I can understand the kid saying, I'm never going to use algebra. I can't understand him saying, I'm never going to use the English language. Think of how many kids don't know what is implied by A implies B. In other words, if B is true, does A have to be true? If B is false, all of these little things. What's the difference between if and only if? This is where these important things come in. In other words, someplace along the line, I don't care how many formulas you know, you have to know when and where to use them. Let me again try to give you a non-mathematical example. Back in somewhere around the 5th grade, I learned what I now call dueling adages. I don't know if anybody else has coined that phrase or not. I may have talked about this last time also. These are adages that contradict one another. He who hesitates is lost, but look before you leap. Absence makes the heart grow fonder, but out of sight, out of mind. Now suppose you're involved in a political election, and there's a certain item that you're very interested in, and two people who are politically opposed are going to be speaking on it. You go to the rally, whatever it is, the town hall, and the first one gives a brilliant speech. You say, this guy is fantastic. I really, really like that. But the speech was based on look before you leap. Now you hear his adversary, another brilliant speech. But it was based on look before the opposite, the dueling adage. They both make sense. What you have to have the ability to decide is in that particular scenario, which of the two is the more appropriate to use. In other words, here you have two perfectly good rules, but no rule to tell you which one to adopt. It reminds, of course, with the World Series going on, I guess it's just being over. I guess it's okay to use a baseball anecdote. It's one of my favorites. It's about the three umpires who were discussing how they call balls and strikes. The youngest umpire said, some are balls, some are strikes. I call them as I see them. The middle-aged umpire said, son, you got it all wrong. He said, some are balls, some are strikes. I call them as they are. And the old umpire got up and said, boys, you both missed the point. He said, some are balls, some are strikes. But until I calls them, they ain't nothing. And that's the whole thing about decision-making. It's very objective once the umpire raises his hand, whether it's a ball or a strike. But which hand he raises is subjective based on how he sees the pitch. So these are the kind of things that come up in logic. It's not just a logical argument, just the fact that the argument is valid, and therefore the conclusion follows from the assumptions, doesn't mean that you've used the right assumptions. These are all things that we should be educating the public on, educating the kids on, giving them stuff that goes beyond the subject, because let's face it, the kid who's majoring in English Lit, if he's lucky, won't forget the quadratic formula until after he passes the test. You know, I think I mentioned last time that my definition of education is the part that's left after you've forgotten everything else. And if you think about that, the number of kids who pass a course and then even 2 or 3 months later don't even remember what the course was about. The third ingredient in terms of human endeavor is the one which I think is extremely important because it really separates us from the rest of the animal kingdom. And what it deals with is the ability to think aesthetically. That despite all of the applications in life, despite all of the grubby things we may be doing, deep down inside, there's an aesthetic sense of values that's in all of us. In fact, there's also a nice anecdote about that involves the late Samuel Eilenberg, who was a brilliant topologist, but he also had a great knack for applied mathematics. I believe he was involved in the Manhattan Project, or maybe one like it, but he was very, very well known for being a good applied mathematician. And people said to him, Sam, you're such a good applied mathematician. Why do you keep staying in pure mathematics? And I may be missing the exact wording here, but Eilenberg's reply was, look, I compare myself to an aesthetic tailor. Sometimes I make a jacket that has 42 different colors. Sometimes it might have 20 different sleeves. Every once in a while, I make a traditional jacket with only one color and 2 sleeves. And if a fellow human being comes into my tailor shop and tries on the jacket, and he likes it, I give it to him as a present out of the goodness of my heart. And that's the way I look at what a math course should be, even for people who are interested in math. People who aren't interested in math should see the brilliance of some of our scientists. Avogadro's number comes up as examples sometimes in the math course that emphasize scientific notation. 6 times 10 to the 23rd. Pretty big number. How big is it? If you could write 1 billion tally marks per second, it would take close to 1 million years to represent that number in tally marks. Who in the world would have the kind of imagination that would believe you would need a number that big. That sounds like a humanist. And yet the whole kinetic theory of gases hinges on that. Isaac Newton. Think about that. I'm going to give you a quotation. Or you can say this to anybody. I'm going to give you a quotation, and based on that quotation, tell me whether it was a scientist or a humanist who said it. Any two objects in the universe, no matter how insignificant, exert an influence upon one another. And if you stop there, people say, well, it's a humanist. So wait, I haven't finished yet. With a force directly proportional to the product of their two masses, and inversely proportional to the square of the distance between their centers. It didn't happen overnight that Newton looked, what's the proverbial thing? He got hit on the head with an apple. He didn't get hit on the head with an apple at 9 a.m. and computed the escape velocity from the Earth's atmosphere at 10:15. It didn't happen that way. But imagine the imagination to be able to say that as I'm looking into this computer screen, we're attracting one another. The two pencils lying on the table are attracting one another. It doesn't sound, I mean, the difference between Shakespeare and Newton is when Shakespeare writes Romeo and Juliet, and you say, hey, wait a second, in this generation, couples are doing that all the time, but they're not committing suicide over it. You say, wait a second. You don't go by the storyline. You go by the poeticness, the great expressions that Shakespeare uses. On the other hand, if Newton states the theory of relativity, of universal gravitation, and it doesn't work, what do you say? Oh, I could make up a scientific theory too if it didn't have to work. Newton has, Einstein had great imagination, but they had to be able to convert it into things that made a huge difference in the real world. And we're not teaching that enough, in my opinion. Even in a math, I remember the first time somebody said to me, the square of an odd number leaves a remainder of 1 when divided by 8. And why was that the only possible thing? When you divide by an odd number by 8, the remainder should be 1, 3, 5, or 7. Why did it always come out to be 1? Well, there was a simple algebraic proof of that, thing that I would never have thought about without that. When did I become interested in plane geometry? When I saw things that boggled my mind. I wasn't thrilled with proving that the base angles of an isosceles triangle are equal. Heck, you just look at the triangle, you can see they're equal. The beauty of plane geometry was that with 10 rules of the game, 5 of which were called axioms, 5 of which were called postulates, Euclid derived book after book of inescapable conclusions. So that's why he's called the father of modern geometry, even though he lived thousands of years after the pyramids were built. How could he be the father of geometry if the ancient Egyptians had already been building pyramids? And it was because of the logical structure. So what happened in my case, I got hooked on geometry when I was assigned a problem that said if the midpoints of a quadrilateral are joined in succession, the resulting figure is a parallelogram. I said, that's impossible, because I can jiggle that quadrilateral, it won't work all the time. And so before I even tried to prove it, I was going to show a counterexample. And I couldn't. And then I saw the geometric proof. It was so easy. In other words, that had to be true based on these 10 simple rules of the game. And these are the things that we're leaving out today. I've seen my grandson's playing geometry book. It's more algebra than it is geometry. They tell the kids things rather than have them see how they are deduced formally. But anyway, I think that's enough for that topic too. I would estimate we have about 10 or 15 minutes left. So now I would like to talk to you beyond the curriculum. I want to talk to you about my love of the community college and what I believe your love is, either implicit or explicit. You may not even realize it. I think I told you last time that what hooked me on leaving the MIT graduate school as a teaching assistant to come to Corning Community College was the word community. Remember, in those days, this was 1958, only about 20% of a high school graduating class went on to college. And so I wanted to do something for the other 80%. When I got to Corning and started teaching, and I suddenly realized that everybody in the community who paid taxes was helping to support the college. And so I said, look, at MIT, my classroom was MIT. I had to be available for my students and for their parents because they were paying a terrific amount of tuition, not as terrific by today's standards, but still a good amount of tuition. And I owed it to my students to be available, not just to them, but to their parents, etc. When I got to the community college, I had that same obligation, plus the fact that I now owed it to everybody in the community because their money their tax money was helping to support the college. I didn't care what group asked me to speak. I went as an ambassador of the college, just a math professor, but the people who heard me, I was the only person perhaps that they knew from Corning Community College, and they viewed the whole college in my image. I knew that I had to do something to let them know how we cared about them. See, it's nice to have a catalog that you send out to the public showing all the nice things that are happening on your campus. But for the person who's paying property taxes to support the college but doesn't have any of their family members attending the college, why should that thrill them so much? So, for example, I made a website just so that people, this was in Corning, not Corning, in Boston, because I wanted the families of people who weren't coming to the college to see that we were doing something for them. For example, there are many kids who aren't coming to the community college who are still deficient in math, and they're going to go to an expensive university, maybe taking the equivalent of what we call remediation. They'll give it a fancier name there. Why should a kid have to be losing valuable time to learn? Just because they have that kind of a problem. Why not? I made myself available so that any family could look at the website and help their children, etc. I realized that the students who we got, even though we got them at all levels, but the majority were the most at-risk students, we were the ones who saw all the problems that they had and the like. I saw myself as a great ambassador to the public schools in the area to help them by showing them what the problems were with the students who we got and how they could have the supplemental resources that might help the kids overcome that. I would talk to people from Corning Glass, from Ingersoll Rand. What kind of courses can I develop for your students? You see, an interesting thing about community colleges, it's different from the university. In a community college, I think it's a fair assumption, at least it was when I was involved with it, that about 85% of the kids who graduate are going to remain local. Now, local communities have different industries and different points of attraction. For example, in Corning, we had the glassworks. So having courses in glassware technology, blowing up, whatever it happened to be, that would be a natural course to have at Corning, but maybe not in Atlantic City. But in the meantime, Atlantic City has gambling casinos and the like, and even if you don't like gambling, a lot of kids could make a living professionally by working in some capacity in a gambling, in one of the casinos. Okay? And so it become natural in Atlantic City to maybe have specialized courses in, I don't know, probability, whatever it happens to be. In other words, the word community goes beyond just education. So in other words, I may have a good overall feeling about what's happening in the nation, but you at the college that you're at knows that community better than I do. I hope my material helps you and it helps the community. But that doesn't mean it has to be restricted to that. You may know, You can establish relationships better with, and maybe you already have, with the K through 12 teachers, to share with them things that you think will help them, listen to what their problems are, go out to the local industries and find out what you can do to help them. And remember, it doesn't all have to be in-house. That's the beauty of the internet. You can make up courses taking piece by piece things from different things that are on the internet for the students to use, for the industries to use. We can tailor-make developmental programs. Very often when kids are in a developmental program, it's because of one or two items. They don't need the whole course. So make up specialized tests where students only have to get remediation or further development. I hate the word remediation, but further development for various topics. You can mix and match modules for people in the industry who need special courses. In other words, in one type of industry, you may need one particular topic, but not another topic. There's all sorts of stuff that we can do. And that's my feeling. In other words, my website is available. It's just one more supplementary resource. I hope you'll use it. But you don't have to. You may have better resources. You may want to develop your own resources. It's amazing how many students fail a course, not because they couldn't do it, but the pace at which they were able to internalize it was slower than the lockstep pace of the traditional classroom. If a student has no idea of what you were talking about at 9 a.m. on Monday, why should you expect that they'll have a good idea by 9 a.m. on Wednesday? But what you could do, and maybe you're already doing it, is using the internet, using your own videos to allow the student to have something to look at in between the classes. I mean, I go even one step further. I allow students to take a test whenever they're ready. They have to come to class because even if you're behind the lecture, you may learn something by seeing what comes ahead that'll help you understand what you're having trouble with now. And if you're ahead, it doesn't mean that you saw all the fine points. You know, even when a student gets 100 on an exam, it's only 100% of what was asked. There are many fine points that we teach that are so subtle, so important, that we don't know how to word them enough to put them on an exam. Notice how much of the exam is based on, can you do these problems, rather than do you understand why your method works. I've had emails from people who are in advanced math, people who are already scientists and engineers, talking about how they really learned more about differential equations, a subject that I'm lousy at compared to professional mathematicians, because I showed them where each of the recipes that they used came from. Many of them wrote to me and said, when I was in school, they told me, this is the equation you use for this kind of a problem, this is the equation you use for that kind of a problem. And they said, we never saw the understanding of how do we know that was what we were supposed to use. They do the same thing. Almost everything they do comes from a handbook. They trust the mathematics without fully understanding it. I've had people write to me saying that if they had understood the mathematics better when they were in school, they'd have done even better in their professional lives. And by the way, if you don't, just go to YouTube, Google my name, Calculus Revisited, look at, don't watch the lecture necessarily, read the comments that students have made about it. And this all came from a community college professor. When I made those videos, my only full-time teaching had been at Corning Community College. I might not even have thought of the present website if I had stayed in an MIT environment, because the students there weren't having those problems. We really are the Statue of Liberty for those kids who otherwise might have been academically disenfranchised. Anyway, that's about all I do. I mean, I'd love to talk to you almost forever. My son once told me if it wasn't for students, teachers would just be people who talked a lot. But I love sharing. I'm very proud of the fact of the role I played in the forming of AMATYC. What I want to show you, it's one thing to philosophize, it's another thing to put it into action. Our next webinar, which will be, I believe, December 1st, I'm not positive, I think that's the date, will be by my two very wonderful colleagues, Judy Bender and Rick Medeiros, who have helped me develop the website in one form or another, to have them show that all the things I talked about in the first two webinars is present in what I've done on the website. In other words, this is not just me talking, saying what could be done, it's what I've put my faith into. In other words, I've thought enough of what I'm doing that I don't mind it being seen by people all over the world. And I'm not worried about what they're going to say. I worry more about the people who could have benefited from my website, but will never know that it existed. That's why I need your help. That's why I would like you to take ownership of some of the work that I've done, add some of your own, and really make this voice that the community colleges may be different than the university, but they're also equal to it in terms of what we do for society. And I think that's probably a good place to close. And I just want to thank you for putting up with my monotone. I hope it was worth your while. And I know I've enjoyed doing it. And I use that, especially at my age, at being 87, I hate to squander an hour. And so if I use the hour wisely, I'm very thrilled when I can say, I wish I had more time, but I couldn't have used that hour any better. I hope you somehow have the same feeling, but I am very thrilled to have had this chance to address you. I still feel awkward that I don't see you face to face, and I'm able to, anyway, just thank you for being with me. And please, please write to me if there's any question or if there's something you want to discuss. I am just delighted to share whatever I know with you. Okay.
Thank you so much, Herb. You're already getting some thank yous in the chat window, and I'll be sure to share that with you after the webinar. So attendees, don't leave quite yet. We have a little bit of bookkeeping to take care of here with the closing of the webinar. Go ahead and get back to my slides. Thank you again for participating in today's webinar. If you'd like to support future AMATYC webinars, please consider becoming a member of AMATYC. And the bit.ly join AMATYC does work. I tried it out today. We are on social media. Check us out on our Facebook page. We do also tweet. Looking for past recordings, so this past recording of Herb's webinar as well as others are located at bit.ly/AMATYC-webinars. And usually it takes us about a week or two to produce and upload these. So today's, for example, it'll take us a couple days, maybe a week to get this up for you as well. Please take a couple minutes here. We've got 2 minutes to evaluate the webinar. I also have the form in there if you want to have a certificate saying that you were in attendance today. That is part of the survey. So we're going to go ahead and go to that bit.ly. I'm going to stop the recording and I'll put that link in the chat window for you so that we can tie this up today.